this lecture, we'll be discussing what is perhaps the most intuitive thermodynamic concept out of all the ones we cover in this course. It's a concept that you know and feel every minute of every day, and you probably check its value multiple times per day. It's the thermodynamic conversation starter, since many of us bring it up when we're not sure what to say. Like, for example, it's cold out there today. Of course, we're talking here about temperature. This variable is of utmost importance in thermodynamics. After all, how could we study heat in motion without a way to know if something is hot? And yet, as we'll see in this lecture, the very notion of temperature may surprise us. In order to truly understand temperature and the fundamental reasons for it, we'll need to head all the way down to the scale of the atom. But before I go down to that scale, I want to motivate this understanding of temperature even more by introducing to you our very first thermodynamic law for this course, called the 0th law of thermodynamics. Notice that it's the first law we're learning, but those wacky thermodynamicists wanted to start counting their laws at 0. So they call this one the 0th law. The law is related at its core to temperature, and it goes as follows. Imagine we have 3 objects. Let's call them object A, object B, and object C. Now, let us place object A in contact with object C. And let us also place object B in contact with object C. The 0th law of thermodynamics states that if objects A and B are each in thermal equilibrium with object C, then A and B are in thermal equilibrium with each other. Equilibrium here means the point at which the temperatures become the same. And it's a concept I'll go into much more deeply in the next lecture. Now, I know that you're probably thinking, well, of course, isn't that law kind of intuitive? Well, yes, it is, but it's important and foundational to state it as a law. It allows us to define and measure temperature using the concept of thermal equilibrium. And importantly, it tells us that changes in temperature are thermodynamic driving forces for heat flow. From the 0th law of thermodynamics, one can define temperature as that which is equal when heat ceases to flow between systems in thermal contact. This is the foundational framework for thinking about energy in its many different forms. Okay, so now let's discuss how we experience temperature, and more importantly, how it is measured. In the most general terms, temperature is a measure of how hot or how cold a body is. Of course, you may be thinking that hot and cold are completely relative terms, and you'd be absolutely right. Ice cubes are colder than boiling water, but they're a whole lot hotter than liquid nitrogen. And that first warm spring day of the year somehow feels much warmer than the rest of spring. So temperature is meaningful only when it is relative to something. That's a really important statement, so I'd like to repeat it. Temperature is meaningful only when it is relative to something. And this very simple but powerful statement leads us immediately to a particular need. That is, we need to define a temperature scale. Now, we've all probably heard of the Celsius and Fahrenheit scales. Here in the US, for some reason, we still use Fahrenheit, while in just about all the rest of the world, the Celsius scale is used. Kelvin is another scale used to measure temperature, and this is known as an absolute scale. It's the standard temperature units of thermodynamics, but we'll come back to that in a moment. A temperature scale allows us to measure relative changes. Now, if you take a look at Celsius versus Fahrenheit, you can see that both the numbers and the relative differences between them are different. In other words, in this comparison, one scale is not just a rigid shift from the other, but rather each degree means something different. So the 100 Celsius degrees between water freezing at 0 and water boiling at 100 are equivalent to those 180 Fahrenheit degrees between 32 and 212. To convert between Fahrenheit to Celsius, we take the Fahrenheit reading, subtract 32 degrees, and multiply by 5/9. as many of us learned early on in school. Now, as I mentioned, in the US, okay, I suppose I should also include the Cayman Islands and the Bahamas. We're all used to the Fahrenheit scale. So when we take our body temperature, a reading of 98.6 is normal, and a chilly day would be around 50 degrees. For the rest of the world, since they're used to the Celsius scale, a normal body temperature is 37 degrees, and that same chilly day would be around 10 degrees. Same exact meanings, just different scales, and therefore different numbers. The history of the Fahrenheit scale goes back to Daniel Fahrenheit, who in 1724 was trying to develop a systematic way to measure differences in temperatures. What he needed were reference points, things that seemed to happen at the same temperature with pretty high consistency. He decided water was a really good candidate for this, so he picked 3 reference points related to water. First, because he had observed that salty water has a different freezing point than fresh water, he chose the temperature at which salt water freezes. That is, when it transforms from a liquid into a solid. He called this 0 degrees. Second, he chose the point at which just plain water without the salt freezes. He called that 32 degrees. And third, he picked the temperature of the human body, which at the time he called blood heat, and referred to it as 96 degrees. The reason for this particular value of 96 was that it meant there would be 64 degrees between that reference point and the freezing point of fresh water. The choice of 64 integrals was not arbitrary. He picked it so that it would be easy to divide by 2 up to 6 times. 2 to the 6th power is 64. Simply put, it made for easier math, and he also wanted this difference to be exactly twice the difference between the freezing points of salty and fresh water. Later, other scientists decided they wanted the boiling point of water to be exactly 180 degrees higher than the freezing point. So they set that as a reference point, which in turn brought up the body temperature reading to 98 instead of 96 degrees. Now, why am I giving you this history? Well, first of all, to give old Fahrenheit his due, but also so that you can see that these temperature scales are really quite arbitrary. Choices are made regarding reference points, and so a scale is defined. And perhaps not surprisingly, historically, a number of different scales have been introduced. For example, in addition to the 3 I already mentioned, Fahrenheit, Celsius, and Kelvin, there's also the Rankine, Newton, Delisle, and Romer scales, to name just a few. By the early 18th century, as many as 35 different temperature scales had been devised. The Celsius, or centigrade scale, was created by Anders Celsius in 1742, and it was presented in a paper he wrote titled Observations of 2 Persistent Degrees on a Thermometer. Notice the word persistent. Again, because a good temperature scale should have as its reference points phenomena that repeatedly happen at the same temperatures. In this case, the phenomena he chose were the freezing and boiling points of water. Although in his original version, freezing was at 100 and boiling was at 0. Later, others decided to reverse these 2 reference points to the Celsius scale we know today, where 100 degrees is boiling and 0 is freezing. Okay, so those are the 2 scales the world uses. Fahrenheit, for the roughly 320 million people living in the United States, Cayman Islands, the Bahamas, Palau, and Belize, and Celsius for the 6.7 billion people, give or take a few, living everywhere else. But regardless of the scale we use, what is it we're actually feeling when we feel, or really I should say measure, a temperature? In order to answer this, we'll have to turn our attention to a definition some of you may have already learned from an introductory physics course, namely the definition of the energy of a moving body. This energy, that is, the energy due to motion, is called the kinetic energy. And the average kinetic energy of an object is defined as 1/2 mv squared, where that m is the mass of the object and the v is its velocity. If we have a bunch of objects, then this definition still holds. The average kinetic energy of the collection of objects would simply be the average of 1/2 mv squared over all of the different objects. Now, let's remember that all matter, whether solid, liquid, or gas, is made up of atoms. We'll be talking about atoms at various points in this course, and I'm sure many of you have seen the periodic table of the elements, which shows all the various atoms that we know about. These atoms are the building blocks for all of the things we know and love, including ourselves, by the way. We're made up of a whole lot of carbon, plus oxygen, hydrogen, nitrogen, calcium, phosphorus, sulfur, sodium, and magnesium, among a bunch of other things. So when we go back to our definition of kinetic energy, and we consider those moving objects to be the atoms that make up a material, well, that's where we get to a crucial part of our understanding of temperature. By measuring temperature, what we're actually doing is measuring how fast the atoms in a material are moving. Okay, that was so important, I'd like to repeat it. When we measure temperature, we're measuring how fast the atoms in a material are moving. The higher the average velocity of the atoms, the higher the temperature of the material. And just to be sure we really feel our oneness with this idea, let's take a look at my Brownian motion table to help bring home the point. So as I talked about, temperature arises fundamentally from the random vibrations of atoms. Now, this is related to the concept of Brownian motion, which means just the motion, the random motion of particles. And since we're talking about the scale of the atom, it means the random motion of the atoms. And that's what gives rise to temperature. So to visualize this, what I have here is called a Brownian motion table. Now, it's a really cool thing as a thermodynamicist to have one of these things, because basically what it does is it reproduces the effects of those random motions. Okay? So this is basically like an air hockey table that you might have seen in an arcade, but it's a much smaller size. And what I'm going to do is I'm going to turn on this pump, which blows air through tiny little holes on the top. And then I can imagine that these are atoms, and I put them on top of the table, and we watch them moving around randomly. Okay? So that's random motion, bumping around. But as I put more on, they don't just bump off the sides of the box, they actually bump off each other. And as I put more and more on, you can see them moving around with different speeds, bumping around off of each other and off of the container walls. This is a very nice intuitive picture of what's happening to atoms as they bump around off of each other and off of the container walls. And you can see that I could put different size atoms on this Brownian motion table, and they'll have different speeds and different trajectories, okay? But notice something really important. The speeds are not all the same. So every one of these is moving at a different speed, and then the speed changes as they get bumped into by others. The temperature is only the average over all of these particles, and that is a constant for this table. If I let it go like this, the temperature is staying the same, even though the particles are changing their speeds, because temperature is only an average over all of the particles. Even when I add more particles to the table, you can see that what happens is the speed of the particles does not change as I add more. But what does change is how often they bump into each other. That is the collision rate. But that's not related to temperature. That is related to pressure. So there we saw an example of particles moving around randomly with different individual speeds. But for the whole table, the average speed was roughly a constant. I hope that gives you a feel for the meaning of temperature, which corresponds to that macroscopic average. And notice that if I turned off the air for the table, all of the particles would have come to rest. What would the temperature in that case be? This question brings us to another temperature scale called the Kelvin scale. And it is the temperature scale of thermodynamics. For that matter, it's the temperature scale used in science and engineering in general. And it's the one that we'll use throughout this course. It's a scale that makes a lot of sense and also makes solving problems in thermodynamics easier. Notice from our definition of temperature as the average kinetic energy that the lowest possible temperature value is 0. This happens only if the average velocity of a material is 0, which would mean that every single atom in the material is completely motionless. The Brownian motion table was turned off. We know that the square of velocity can never be negative. And since the mass cannot be negative either, the kinetic energy is always a positive value. So 0 is the lower bound on temperature, and it's the critical reference point in the Kelvin temperature scale, often referred to as absolute 0, since there's no possibility for negative values. So the Kelvin scale, named after Lord Kelvin of Scotland, who invented it in 1848, is based on what he referred to as infinite cold, being the 0 point. The Kelvin scale has the same magnitude as the Celsius scale, just shifted by a constant of about 273 degrees. So 0 degrees Kelvin, remember, corresponding mathematically to the lowest possible value of temperature, is equivalent to about negative 273 degrees Celsius. Well, negative 273.15 to be precise. So a nice comfortable temperature for us humans would lie at around 298 Kelvin, corresponding to 25 degrees Celsius or 77 degrees Fahrenheit. Now I know that 298 is a strange value to think of as feeling like a warm sunny day for many of us not used to the Kelvin scale. But the Kelvin scale is fundamental because of the fact that it has built into it the notion of an absolute 0. In fact, the Kelvin scale is so central in thermodynamics that it's often referred to as the thermodynamic temperature scale. Okay, so we know that the average speed of particles that make up a system is related to the temperature of the system. This is an example of connecting a macroscopic property to a microscopic property, something that we discussed in our last lecture. In this case, macro relates to the single value we measure to describe the system, its temperature. That corresponds to an average over all those micro quantities, the particle velocities. For example, here's a distribution of velocities of different atoms at room temperature, or to be precise, 298.15 Kelvin. The x-axis corresponds to the velocity of the particle, and the y-axis is the probability that the particle has that speed. Note that all of these atoms are gases at this temperature. Also notice that the lightest atom, helium, has a more spread out distribution of velocities and can reach much faster speeds, while the heavier atoms, like argon and xenon, have a sharper peak, so less of a spread in velocities and tend to be slower on average. This type of relationship is known as a Maxwell-Boltzmann distribution, which gives us a distribution of particle velocities that depends on the temperature and pressure of the system, as well as the masses that make up the particles. By the way, did you notice how fast those atoms are moving at room temperature? 500 meters per second, just for reference, is 1,118 miles per hour. As we'll see, these average distributions of velocities of atoms form a basis for understanding how often they collide with one another, which gives us another crucial macroscopic thermodynamic variable, namely pressure. But I'm getting ahead of myself here. For the rest of this lecture, I want to stick with temperature. So, now that we know what temperature is, all the way down to the scale of the atom, let's take a look at how we actually measure it. How is it that we determine how hot or cold something is? As you all know, of course, the answer is to use a thermometer. A thermometer works using the principle of thermal equilibrium. And there's that really important thermodynamics concept I mentioned earlier when I told you about the zeroth law. Equilibrium means that the system is no longer changing on average. So if we measure the temperature of the system, then even though the various atoms could be changing their individual velocities, either slowing down or speeding up, the average over all of the velocities stays the same. This is the state of equilibrium at the macroscopic scale. And it's a concept we will use a lot in this course. So thermal equilibrium is important for measuring temperature, since if I place a thermometer in contact with an object, after some time, the reading on the thermometer reaches a steady value. This value is the temperature of the object, and it is the value at which the thermometer is in thermal equilibrium with the object. One of the earliest records of temperature being measured dates all the way back to the famous Roman physician Galen of Pergamum, who in the year 170 AD proposed the first ever setup with a temperature scale. He used equal quantities of boiling water and ice, which he called neutral temperature. And on either side of this point, he had 4 degrees of heat and 4 degrees of cold. Although Galen attempted to quantify and measure temperature, he did not devise any sort of apparatus for doing so. For that, we have to fast forward more than 1,400 years to the time of Galileo. In the year 1592, Galileo proposed the thermoscope, a device that predicted temperature fluctuations by using a beaker filled with wine plus a tube open at one end and closed with a bulb shape at the other. If you immerse the open end of the tube into the beaker of wine, as shown here, then the bulb part is sticking up at the top. With this instrument, if the temperature gets warmer, the air inside the bulb at the top expands, and the wine is forced back down the tube. While if the temperature gets colder, the air inside the bulb contracts, making the wine rise up in the tube. Now, if we were to engrave marks onto the side of the glass tube, something that was not done until 50 years later, then this thermoscope becomes a thermometer. That is, it becomes a way to measure and quantify changes in temperature. A little bit later, a more sophisticated kind of thermometer was developed, called a Galilean thermometer. Although there is compelling evidence that it was not actually invented by Galileo himself, but rather by his students at the Accademia del Cimento, or Academy of the Experiment. Although most people still refer to it as a Galilean thermometer, the term Florentine thermometer is perhaps more accurate. Let's take a look. The key concept in such a thermometer is that the density of water depends on temperature. By density, I mean the mass of water divided by its volume. At room temperature, this value is just under 1 gram per centimeter cubed, 0.997044 to be exact. The point is that this density changes as the temperature changes. Now, if I place an object in water that has a greater density than the water, well, then it will sink to the bottom, while an object with density less than the water floats up to the top. If the object's density is exactly equal to the water density, then it rests in the middle of the container. Using this principle, the Florentine thermometer was constructed, and it looks something like this. 5 bulbs of different densities are used in this case, each one carefully calibrated to be exactly equal to the density of water at a particular temperature. The bulbs are then placed in a tube filled with water. So, if the temperature is, say, 76 degrees Fahrenheit, the bulb representing 76, that is, the one whose density matches the density of water at exactly 76 degrees Fahrenheit, that bulb floats around in the middle, as shown. While denser bulbs, that would be 64, 68, and 72 degrees in this case, sink down to the bottom, and the lighter bulb, corresponding to the density of water at 80 degrees, floats to the top. The bulb floating in between gives the temperature reading. Now, let's change the temperature by applying heat to the outside wall. This changes the temperature of the water inside, which in turn changes its density, making it decrease, which in turn causes the less dense bulbs to sink further. Notice that the reaction of this thermometer to temperature change is quite slow, not exactly ideal for measuring temperature. This thermometer also requires a rather large piece of equipment. Imagine if you wanted to know the temperature to an accuracy of a single degree in a range from 0 to 100 degrees. You'd need 100 balls inside a pretty big container. And yet, compared to previous thermometer designs, the advantage of this new design was that since it was based on a fully sealed liquid, the pressure of the air outside didn't change the temperature reading, as it did with the older air thermoscopes. Taking the idea of a fully sealed liquid even further, the next type of thermometer that was developed was still based on the change in density of a fluid with temperature, but now the effect was exaggerated by the geometry of the design. As you can see here, the fluid fills a small glass bulb at one end and is allowed to expand or contract within a tiny, fully sealed channel stemming out from the bulb. Many of us are quite familiar with this type of thermometer and have in fact had our temperature taken with it many times. Mercury was the fluid of choice for a long time, since it expands and contracts in quite a steady manner over a wide temperature range. This is a good thing for a temperature measurement apparatus, since we'd like the measurement of a degree to be the same, whether it's taken at 60 degrees or 80 degrees. But various alcohols maintain the same steady expansion and contraction versus temperature as mercury does, and since mercury is poisonous, it has largely been phased out as the thermometer's working fluid of choice. And you may be thinking, why not use water as the fluid? Well, an advantage of alcohol over water is the larger temperature range for which alcohol remains a fluid. For example, ethanol, which is the fluid inside the thermometer I just showed you, can be used to measure temperatures all the way down to minus 70 degrees Celsius, while water, of course, would have frozen at 0 degrees. These types of fluid-filled glass thermometers, based on essentially the same original Florentine thermometer designs, remained the dominant temperature measurement devices for centuries. And in fact, it is these types of thermometers that were used to develop the most important temperature scales that we've already discussed. More recently, though, new temperature measurement techniques have emerged, ones that are even more accurate and can span a wider range of temperatures. One such type of thermometer some of you may be familiar with is also based on volume expansion. But in this case, the material being expanded is a solid metal as opposed to a liquid. By placing two thin sheets of different metals together, this bimetal strip works as a way to measure temperature, since as the temperature changes, the two metals expand and contract differently. Since one strip expands more than the other, and since the two strips are glued together strongly, they will tend to bend. By calibrating this bending, one can measure temperature. And bimetal strips are useful because since they're made out of solid metal, they can go to very low as well as very high temperatures. It's the kind of thermometer you might find in your thermostat at home, or like this one here, which you can safely stick into your turkey in the oven. Note that regardless of the type of thermometer, it must always be calibrated. A device that is not calibrated will simply show an increase in numbers when heated and a decrease in numbers when cooled. But these numbers have no physical meaning until reference points are used to determine both what the actual temperature as well as changes in temperature mean. In the case of the bimetal strip, a certain bend may be calibrated with the boiling point of water, while a change from this bend to another reference point, say the freezing point of water, would indicate how much bend corresponds to each degree. Now, it's important to keep in mind that we don't necessarily always need to have a thermometer that gives us the most accurate temperature and over the largest possible range. It depends on how we plan to use the thermometer. For example, in many third world countries, low cost is the most important factor for technology to become useful. So if one could measure temperature within only a very narrow temperature range, but for extremely low cost, it would be quite valuable. That's exactly the case for these liquid crystal thermometers, which respond to temperature change by changing their phase and therefore color. I simply take one of these strips, which costs less than a penny, and place it on my forehead to check my temperature. And the last type of thermometer we'll examine here is called an infrared or IR thermometer. The key principle of this type of temperature measurement is that by knowing the infrared energy emitted by an object, one can determine its temperature using a theory related to what is called blackbody radiation. Now, I'm not planning to cover blackbody radiation here in any sort of detail, but I just want you to know that from this theory, we know that any material with a certain temperature emits energy. So an IR thermometer captures this energy and then converts it into an electrical signal. From this, a corresponding temperature value can be derived using one of the equations from the theory of blackbody radiation. So to use this thermometer, I simply point it where I want to measure, and I get an almost instant reading of the temperature, as you can see. Notice that this IR thermometer points a red spot to where it's measuring the temperature. That's just coming from a laser pointer built into the thermometer to make sure we know where it's measuring. But it has nothing to do with the measurement itself. People have been confused at times by this part of the thermometer and even refer to it as a laser thermometer, but rest assured, this is not measuring temperature using a laser. Now, in contrast to the super cheap liquid crystal thermometers, these IR thermometers are quite expensive. However, they do possess many advantages, such as high accuracy over a very wide temperature range, the possibility to collect multiple measurements from a collection of spots all near one another, creating an effective heat map, and the ability to measure temperature from a distance, so not in direct contact with the object. And speaking of being in thermal contact, that brings me back to the very final point of this lecture, namely a reminder of the zeroth law of thermodynamics. Remember, if we have two objects A and B in thermal contact, then A and B will come to thermal equilibrium. That is, they will have the same temperature. If a third object C is then brought into contact with either one of these, then this object will have the same temperature as both objects A and B. All three of the objects will come to thermal equilibrium with one another. This law seems kind of intuitive, but importantly, it tells us that changes in temperature are thermodynamic driving forces for heat flow. The concept of temperature itself is based upon the zeroth law of thermodynamics. As I said before, from this zeroth law of thermodynamics, one can define temperature as that which is equal when heat ceases to flow between systems in thermal contact. This is the foundational framework for thinking about energy in its many forms.